Hello everyone, we're continuing with chapter 5, looking at sections F through I. So there's a whole bunch of theorems we're going to look at today. So let's begin with section F, the remainder theorems. We talked about dividing polynomials by linear and quadratic factors in the previous video. So here we learned that if we divide a polynomial by a linear factor, x minus k, until we get a constant remainder out, that remainder will be equal to the polynomial when evaluated at that value of k. So this is called the remainder theorem. It's a theorem that has to do with a remainder. And I know most of the time I don't bother going over proofs, but I think the proof of this one is extremely straightforward. So, take a little peek at it there. So here, if we divide this quartic function by x plus 2, what's the remainder? So oftentimes we're not really actually interested in what the quotient is. We actually really just want to know what the remainder is. So this is why this theorem is helpful, because we don't need to spend the time doing the long division that we saw in the last video. We can just immediately put in this case, -2 for those x values, and then really quickly we realize, oh yeah, the remainder is 34. This is a very popular IB question type. They've asked questions like this tons of times. We're asked to find two values, A and B. Well, look, we've got two linear factors that we are going to put in here. What are we going to do? We're going to have a system of equations, right? So we put in 2 into this expression, it should be equal to 20. We put in -5 into this expression, it should be equal to 6. And like I said, that gets us a system of equations that's easy to solve, and we can work out what A and B are. If you know the remainder theorem, this kind of question is super easy. If you don't know it, going to be challenging because you're going to have to do a lot of long division, and it's a pain in the butt. So just please be familiar with the remainder theorem. The IB likes it a lot. This one's going to be a little bit tougher. We've got our polynomial being divided by a quadratic. There is no remainder theorem for quadratics. So I don't know. Let's see what we can work out here. For starters, let's divide p of x by this quadratic. We're told what the quotient is. So we can write our polynomial as the quotient multiplied by the divisor plus this, again, unknown remainder. The remainder is going to be linear, however, because it's got to be 1 degree less than our divisor. So next, we're going to use our remainder theorem because I do have two linear factors here that we can work with. And again, that makes sense. There's two linear factors, two unknowns here with the A and B. So I smell a system coming up again. So we put in our +2, we get one equation, put in -1, we get our second equation in terms of A and B, solve the system, no problem. All right, that's really all there is to the remainder theorem. There's no special tricks or extreme challenges that the IB is likely to throw at you, so I feel good at this point. Now we're going to move on to section G, which is about something very closely related called the factor theorem. Now think about this. When something is a factor, that means when we divide by it, the remainder is 0, right? So that's all the factor theorem says. If we've got a factor, when we put in k into p of x, we're going to get 0 out. Again, here's a simple proof if you're interested in it. So for a problem like this, if we're told that x minus 2 is a factor of that, that means we're just going to put in 2 into all that, and it's going to equal 0. Right here, p of 2 equals 0. They say it's using the factor theorem. I think it's really just using the remainder theorem, but whatever. Point is now we can get k equals -2. But part 2 of this problem says, hence fully factorize that thing. So it's a cubic. Factorizing cubics isn't super easy generally, but we know that x minus 2 is a factor, so we just divide by that. We saw how to do that in the last video, and that can get us the full factorization down here. Now you'll often see the factor and remainder theorems in the same problem together. They'll give you a polynomial with a and b, and they'll say, oh, this linear expression is a factor of it, and this other linear expression gives a remainder of whatever when you divide by it, so find the values of a and b. So that's common. But again, if you know the theorems, these questions are super, super easy. So pro tip, know the theorems. Okay, moving on to section H, which is about the fundamental theorem of algebra. Really just if we have an nth degree polynomial, then that polynomial has exactly n zeros. So if we have a linear function that's not horizontal, that's a function of degree 1, and yeah, it's going to have exactly 1, 0. We know every non-horizontal line crosses the x-axis in exactly one place. If we have a quadratic, it should have exactly 2 zeros. Now, a lot of quadratics do, but if they don't, then their zeros may be complex. All right, and we also have roots or zeros that may be repeated. So when you have a quadratic whose vertex is on the x-axis, rather than say that that just has one root, we'll say that it has a repeated root. That way we are aware and we're commenting on the fact that there are in fact two. And if the quadratic has no real roots, if it's a quadratic that's floating up above or below the x-axis, that means that both of its roots are just complex. Now there's a bunch of other facts down there in the blue box at the bottom, but the one that I really need us to focus on is this one right here. Anytime that we have a complex number as a zero of a real polynomial, then its complex conjugate is also going to be a zero. Right now, pretty much everything we do in this course is going to be a real polynomial. I know there's at least questions in the textbook that have like quadratics where the coefficients are complex numbers themselves. I'm not familiar with the IB necessarily doing that in the past or being interested in doing that in the future. I don't know, but I don't remember it, and I don't think they're going to do it. But this is a super important fact, though. The roots are going to come in conjugate pairs, again, as long as the polynomial is real itself. So that's super important, and just knowing up in the top blue box, again, nth degree polynomial, it's going to have exactly n zeros. Easy to remember, I think, and super, super useful, as we'll see. So in this problem, we're given a zero of this polynomial. Since we know 1, 0, that means we're going to have a second zero automatically, right? And they're going to approach this by using the sum and the product of the roots. So we saw this in the last one. By taking these two roots together, we can make the quadratic. We can work backwards to build the quadratic that they came from. Again, they're using the sum and the product to get -6 is going to be negative b over a, and then 10 is going to be c over a. And that's probably the fast way to do it. You could also rewrite it as x minus -3 plus I times x minus -3 minus I, multiply together, combine like terms, you'll still get that quadratic. All right, so that means that our given cubic has to be equal to that quadratic times some linear. We know that it's going to have a constant term of -3 because we've got to get -30 at the end, so 10 times -3 will get us that. And then we just need to figure out what a is. You'd want to we're going to compare coefficients for like terms. We can see from solving 6a minus 3 equal to 9, we can figure out what a is. From there, we figure out what that other linear factor is. It's 2x minus 3, which gives us our third zero of 3 over 2. Here's another one. We've got a cubic again. One of the zeros is purely imaginary. Purely imaginary just means it doesn't have a real part, so we can consider that root to be b times I. Since we know b times I, we know that negative b times I is also going to be a 0. So again, we can build a quadratic factor out of these. This is going to be easier than the last one we saw. That quadratic factor is x squared plus b squared. Again, our original cubic is equal to that quadratic times some other linear factor. That linear factor is going to be a little bit tougher this time. We need to get 15 out as our constant. So that's going to be this b squared times, well, it's got to be 15 over b squared, right? But again, from there, same idea. Multiply through, compare coefficients, and in this case we get a system with a and b, so that's fun. But you can easily substitute in one for the other, so we can solve that system. Again, not too difficult. One real root, two complex conjugate roots. We're at the last section now, section I, which is about the sum and the product of the roots. We actually talked about this back in one of the earlier chapters of the first book for the course, the blue book. We saw the sum and the product of the roots of a quadratic there. But I said in that video, hey, you might as well learn the proper formula now because it can be extended to all polynomials. So we've got a polynomial equation here. This is our polynomial equals 0. Again, just written in sigma form to keep it condensed. The sum of the roots is always going to be the negative of the coefficient of the second term divided by the leading coefficient. The product is going to be the constant term divided by the leading coefficient, then multiplied by -1 to the power of n. So an odd function, it'll be negative, an even function, it'll be positive. Take a moment and compare justify to yourself that these formulas do get you negative b over a and c over a for your sum and product of roots of a quadratic. These formulas are again on page 5 of the formula book, so you don't need to memorize these, but we do need to, know that they're there and know how to use them. So, okay, this is just a simple problem you could look at. Find the sum product of the roots of this. I don't think you're going to get asked a question that's this direct. This one's a little more exciting though, right? We've got a quartic function, c, d, and e are unknowns. We've told a little bit of information about it. We want to know what its other two complex zeros are. And we're given the hint, thank you very much, textbook, to use the sum and the product formula to figure out what m and n are. I would start, however, by using this y-intercept, as the book does. Since we know that, that means when we put in x equals 0 into this, those first four terms drop out. E has to be equal to 180. There we go, they've got that there. Before that, however, they've noted, hey, the sum of the four zeros, because we do know all four of them, it's m plus or minus ni, and then we have 2 and 6. The sum of those four has to be negative 12 divided by 3. So the n's cancel out, and then we can solve for m. We're most of the way there. Moving right along, we've used the sum of the roots, so now let's use the product of the roots, and this is nice since now we already know what m is. We multiply everything together, and that's going to be equal to our constant, which was 180, divided by our leading coefficient of 3, multiplied by -1 to the fourth. Okay, so it's just 180 over 3, 60. And then we're going to solve this for n, which isn't too bad. Down at the bottom, we got n squared is equal to 1. But we know n has to be then positive 1 because we're told up here that n is going to be greater than 0. So we've got our answer. Now, if we didn't have this hint to use the sum and product of the roots formulas to work this out, we might have been tempted to try to do some other stuff. Like you could have put in 2 and 6 into this equation here, set it equal to 0 then, and then you can solve a system of equations. You could figure out what C and D are. It's not the easiest thing to work out without a calculator, but it is doable. And then you should be able to consider x minus 2 and x minus 6 as linear factors, build a quadratic out of that, and then divide this quartic by that quadratic. You should be able to get another quadratic expression out, and then you could set that equal to 0 to work out your other two complex roots, -2 plus or minus I. But that's a lot, so don't do it that way. All right, so that's it for this video. Again, the particular topics in here I don't really think are like super challenging on their own, but they do show up very often. So you absolutely need to know this stuff. Again, we've got the remainder and factor theorems, which are really just the same thing. The fundamental theorem of algebra that just says, hey, if we have an nth degree polynomial, it's going to have n zeros, and they're going to come in conjugate pairs if they're complex. And some of the product roots, that's in the formula book, page 5, so you don't need to memorize that, but you do need to be able to use it.